We've all seen AI get amazing at language, right? It can write poems, it can write code. But what if the next huge leap for AI isn't about finding the perfect word, but about actually grasping the meaning behind it all? Today, we're going to look at a new kind of AI that predicts not what to say next, but what something truly means.
And that brings up a really good question. The AIs that can both see and talk about the world, we call them vision language models, or VLMs. They're incredible, but they have this big, clunky problem. They are so power hungry and so slow. Think about an AI assistant in a pair of smart glasses. If you have to wait for it to tell you what you're looking at, it's basically useless. So what's causing this massive bottleneck?
Well, the heart of the problem is how these models have always been built. They're designed to generate text one single word at a time. And this approach, it turns out, comes with some serious hidden costs that really limit what they can do, especially when you need them to work in real time.
So let's break this down. There are basically two massive roadblocks. First, the training is just ridiculously expensive. The AI has to learn not just the core meaning of something, but all the tiny, subtle ways you could phrase it, like word choice and writing style. It's like trying to teach it red ball by forcing it to memorize every possible sentence that has ever existed about a red ball. It's just not efficient. And second, they're slow. They build their answers one piece at a time, word by word. It's a process called autoregressive generation, and that step-by-step method creates a lag that is an absolute deal-breaker for things like live video analysis, where you need to know what's happening right now.
Okay, so to fix all of this, researchers at Metafair are trying something completely different. It's a new approach called VL-JPA. And the core idea is, well, it's simple, but it's totally revolutionary. What if, instead of training the AI to predict the next specific word, we trained it to predict the abstract meaning of the entire answer?
And this right here shows the difference perfectly. On the left, that's the old way, painstakingly guessing one little piece of text or token after another. But on the right, you've got the GPAT approach. It sees an image, it gets a question, and then in a single efficient leap, it predicts the entire meaning of the answer. It's a huge shift from building with tiny bricks to just capturing the whole idea all at once.
Now, the way this works is by using something called an embedding space. Just picture a giant invisible map where every possible meaning has its own specific location. So on this map, an idea like the lamp is off and the room is dark would be located right next to each other, like neighbors. For an AI, it is so much easier to predict the right neighborhood on this map than it is to spell out the exact street address word by word. And that just fundamentally simplifies the whole learning process.
So, how does this machine actually work? Let's pop the hood and take a look at the JEPA architecture to see how it learns to make these incredibly efficient predictions.
All right, so at a really high level, here's the deal. An image and a question go in on the left side. The system's entire job, its whole reason for being, is to predict that target embedding, that's the specific spot on our meaning map. And notice, producing actual words is an optional final step. It's almost like an afterthought. The real work is done in figuring out the meaning first.
Let's break this down into 4 key jobs. First, you've got the X encoder. Think of it like the system's eyes. It just summarizes all the visual info. Then, the predictor. This is the brain of the operation. Takes that summary and a question, and it guesses the meaning of the answer. During training, it checks its work against the Y encoder, which is kind of like a teacher holding the correct answer key, already translated into meaning. And finally, you have the Y decoder. It's just a translator, turning that final meaning back into human language, but only when we actually ask it to.
Okay, so that's all the theory. But what does this new architecture actually get us in the real world? Well, the benefits in terms of speed, size, and just raw intelligence are pretty staggering.
Let's start with size. In a head-to-head competition, the VL-JEPA model needed 50% fewer trainable parameters. You can think of parameters as all the little internal knobs and dials the AI has to adjust while it's learning. Fewer knobs means a much lighter, more efficient model to both train and run. And to really put that into perspective, a standard VLM in this experiment needed a component with 1 billion of those parameters to work. VL-JPA get better results using a predictor that was half the size, just 500 million parameters. That is a massive, massive efficiency gain.
And it's not just about training, it's also about speed when it's actually running. Because VLGPA isn't forced to generate text for every single frame of a video, it can use this clever technique called selective decoding. And that cuts down the number of really expensive decoding steps by nearly 3 times, without losing any performance. So here's how that works. As the model is watching a video, it's producing this constant stream of meaning. Think of it like a continuous heartbeat of understanding. It only bothers to translate that meaning into actual words when the heartbeat changes in a big way, like when a person starts a totally new action. This is absolutely perfect for something like smart glasses, which need to understand what's happening all the time without completely draining your battery.
Okay, so it's smaller and it's faster, but is it actually better? Let's see how VLJEPA really performs against some of the biggest names in AI on the standard industry tests. Just look at these learning curves. On both of these tasks, the blue line, representing VLJPA, just shoots up way faster and gets higher than the traditional model in red. This shows something called sample efficiency, which basically means the AI learns more from the exact same amount of data. It's not just a better student, it's a faster one.
And this awesome performance also holds up against the best in the business. This table shows zero-shot results. That's when you test the AI on stuff it has never seen before, like a surprise pop quiz. And you can see, across the board, VLJEPA comes out on top against some major established models. The takeaway here is crystal clear. It's not just more efficient, it's fundamentally more capable.
So what does all of this mean for the future of AI? What's the big picture? Well, this research suggests that the most powerful path forward might not be these generative models that just mimic human language, but predictive models that actually understand the world on a deeper, more abstract level. The real-world applications for this are just incredibly exciting. I mean, think of smart glasses that can actually give you help in real time because they understand what you're doing without any lag, or robots that can monitor and plan their actions in really complex changing environments. This kind of efficient, continuous understanding of meaning is the key that's going to unlock all these next-generation AI systems.
And that really leaves us with a final, crucial question. For years, we've basically measured AI by how well it can talk. But what if the true measure of intelligence isn't just about eloquent speech, but about deep understanding? This shift from predicting words to predicting meaning, it might just be the beginning of AI's next chapter.